Hey guys, it's me. I'm back. Let me continue with the book on page 178. Unsigned integers declared unsigned obey the laws of arithmetic modulo 2 power n, where n is the number of bits in the representation. On the PDP 11, unsigned long quantities are not supported. Single precision floating point float and double precision floating point double may be synonyms in some implementations, because objects of the foregoing types can usefully be interpreted as numbers. They will be referred to as arithmetic types. Types char and int of all sizes will collectively be called integer types. Float and double will collectively be called floating types. Besides the fundamental arithmetic types, there is a conceptually infinite class of derived types constructed from the fundamental types in the following ways: arrays of objects of most types, functions which return objects of a given type, pointers to objects of a given type, structures containing a sequence of objects of various types, unions capable of containing any one of several objects of various types. In general, these methods of constructing objects can be applied recursively. 5. Objects and L values. What is this word? I cannot find it on the dictionary online. Is this a real word? No, it does not exist. Objects and L values, okay? That is how it does. That is how it spells. That is how it sounds. An object is a manipulatable region of storage. An L value is an expression referring to an object. An obvious example of an L value expression is an identifier. There are operators which yield L values. For example, if uppercase E is an expression of pointer type, then asterisk uppercase E is an L value expression referring to the object to which uppercase E points. The name L value comes from the assignment expression uppercase E1 equal uppercase E2, in which the left operand uppercase E1 must be an L value expression. The discussion of each operator below indicates whether it expects L value operands and whether it yields an L value. 6. Conversions. The number of operators may, depending on their operands, cause conversion of the value of an operand from one type to another. This section explains the result to be expected from such conversions. Chapter 6.6 summarizes the conversions demanded by most ordinary operators. It will be supplemented as required by the discussion of each operator. 6.1 Characters and integers. A character or a short integer may be used whatever an integer may be used. In all cases, the value is converted to an integer. Conversion of a short integer to a longer always involves sign extension. Integers are signed quantities. Whether or not sign extension occurs for characters is machine dependent, but it is guaranteed that a number of the standard character set is non-negative. Of the machines treated by this manual, only the PDP-11 sign extends, and the PDP-11 character variables range in value from -128 to 127. The characters of the ASCII alphabet are all positive. A character constant specified with an octa escape suffers sign extension and may appear negative. For example, single quote \377 has the value -1. Okay. Hang on. Okay, hang on. When a longer integer is converted to a shorter or to a char, it is truncated. On the left, excess bits are simply discarded. 6.2 Float and double. All floating arithmetic in C is carried out in double precision. Whenever a float appears in an expression, it is translated to double by zero padding its fraction when a double must be converted to float. For example, by an assignment, the double is rounded before truncation to float length. 6.3 Floating and integer. Conversions of floating values to integer type tend to be rather machine dependent. In particular, the direction of truncation of negative numbers varies from machine to machine. The result is undefined if the value will not fit in the space provided. Conversions of integer values to floating type are well behaved. Some loss of precision occurs if the destination lacks sufficient bits. 6.4 Pointers and integers. An integer or long integer may be added to or subtracted from a pointer. In such a case, the first is converted as specified in the discussion of the addition operator. Two pointers to objects of the same type may be subtracted. In this case, the result is converted to an integer as specified in the discussion of the subtraction operator. 6.5 Unsigned. Whenever an unsigned integer and a plain integer are combined, the plain integer is converted to unsigned and the result is unsigned. The value is the least unsigned integer congruent to the signed integer. Modulo Module. How does it pronounce it? How does it pronounce this? Module. Okay, module. 2 power word size in 2's complement representation. This conversion is conceptual and there's no actual change in the bit pattern. When an unsigned integer is converted to long, the value of the result is the same numerically as that of the unsigned integer. Thus, the conversion amounts to padding with zeros on the left. 6.6 Arithmetic Conversions. A great many operators call conversions and yield result types in a similar way. This pattern will be called the usual arithmetic conversions. First, any operands of type char or short are converted to int, and any of type float are converted to double. Then, if either operand is double, the other is converted to double, and that is the type of the result. Otherwise, if either operand is long, the other is converted to long, and that is the type of the result. Otherwise, if either operand is unsigned, the other is converted to unsigned, and that is the type of the result. Otherwise, both operands must be int, and that is the type of the result. 7. Expressions. The precedence of expression operators is the same as the order of the major subsections of this section. Highest precedence first. Thus, for example, the expressions referred to as the operands of plus chapter 7.4 are those expressions defined in chapter 7.1 to chapter 7.3. Within each subsection, the operators have the same precedence, left or right associativity. Left or right associativity is specified in each subsection for the operators discussed therein. The precedence and associativity of all the expression operators is summarized in the grammar of chapter 18. Otherwise, the order of evaluation of expressions is undefined. In particular, the compiler considers itself free to compute sub-expressions in the order it believes is most efficient, even if the sub-expressions involve side effects. The order in which side effects take place is unspecified. Expressions involving a commutative and associative operator asterisk plus ampersand bar yield may be rearranged arbitrarily, even in the presence of parentheses to force a particular order of evaluation, and explicit temporary must be used. The handling of overflow and divide check in expression evaluation is machine dependent. All existing implementations of C ignore integer overflows. Treatment of division by zero and all floating point exceptions varies between machines and is usually adjustable by a library function. 7.1 Primary expressions. Primary expressions involving dot or point, arrow, subscripting, and function calls group left to right. An identifier is a primary expression provided it has been suitably declared is discussed below. Its type is specified by its declaration. If the type of the identifier is array, however, then the value of the identifier expression is a pointer to the first object in the array, and the type of the expression is pointer to. Moreover, an array identifier is not an L-value expression. Likewise, an identifier which is declared function returning, when used except in the function name position of a call, is converted to pointer to function returning. A constant is a primary expression. Its type may be int, long, or double, depending on its form. Character constants have type int. Floating constants are double. A string is a primary expression. Its type is originally array of char, but following the same rule given above for identifiers, this modified to a pointer to char, and the result is a pointer to the first character in the string. There is an expression inserting initializers. See Chapter 8.6. A parenthesized expression is a primary expression whose type and value are identical to those of the unadorned expression. The presence of parentheses does not affect whether the expression is an L value. A primary expression followed by an expression in square brackets is a primary expression. The intuitive meaning is that of a subscript. Usually the primary expression has type pointer to. The subscript expression is int, and the type of the result is the expression uppercase E1 bracket uppercase E2 is identical by definition to. What is this? So confused. All the clues needed to understand this notation are contained in this section, together with the discussions in chapters 7.1, 7.2, and 7.4 on identifiers, asterisk and plus respectively. Chapter 14.3 below summarizes the implications. Here on, a function call is a primary expression followed by parentheses containing a possibly empty, comma-separated list of expressions which continue the actual arguments to the function. The primary expression must be of type function returning, and the result of the function call is of type. As indicated below, a what is this word? A hitherto unseen identifier followed immediately by a left parenthesis is contextually declared to represent a function returning an integer. Thus, in the most common case, integer-valued functions need not be declared. Any actual arguments of type float are converted to double before the call. Any of type char or short are converted to int. And as usual, array names are converted to pointers. No other conversions are performed. automatically. In particular, the compiler does not compare the types of actual arguments with those of formal arguments. If conversion is needed, use a cast. See Chapter 7.2, 8.3. In preparing for the call to a function, a copy is made of each actual parameter. Thus, all argument passing in C is strictly by value. A function may change the values of its formal parameters, but these changes cannot affect the values of the actual parameters. On the other hand, it is possible to pass a pointer on the understanding that the function may change the value of the object to which the pointer points. An array name is a pointer expression. The order of evaluation of arguments is undefined by the language. Take note that the various compilers differ. Recursive codes to any function are permitted. A primary expression followed by a dot followed by an identifier is an expression. The first expression must be an L-value naming a structure or a union, and the identifier must name a member of the structure or union. The result is an L-value referring to the named member of the structure or union. A primary expression followed by an arrow built from a minus or a angle bracket followed by an identifier is an expression. The first expression must be a pointer to a structure or a union, and the identifier must name a member of that structure or union. The result is an L-value referring to the named member of the structure or union to which the pointer expression points. Thus, the expression uppercase E1 arrow most is the same as like this. Structures and unions are discussed in Chapter 8.5. The rules given here for the use of structures and unions are not enforced strictly. In order to allow an escape from the typing mechanism seen Chapter 14.1. 7.2 Unary operators. Expressions with unary operators group right to left. The unary asterisk operator means indirection. The expression must be a pointer, and the result is an L-value referring to the object to which the expression points. If the type of the expression is pointer to, the type of the result is. The result of the unary Ampersand operator is a pointer to the object referred to by the L-value. If the type of the L-value is, the type of the result is pointer to, the result of the unary operator is the negative of its operand. The usual arithmetic conversions are performed. The negative of an assigned quantity is computed by subtracting its value from 2 power n, where n is a member of base in an int. There is no unary plus operator. The result of the logical negation operator. Exclusive is 1 if the value of its operand is 0. 0 if the value of its operand is non-zero. The type of the result is int. It is applicable. It is applicable to any arithmetic type or to pointers. The yield operator yields the ones complement of its operand. The usual arithmetic conversions are performed. The type of the operand must be integer. The object referred the object referred to by the L value operand of prefix plus plus is incremented. The value is the new value of the operand, but it's not an L value. The expression plus plus lowercase x is equivalent to x plus equal 1. See the discussions of addition chapter 7.4 and assignment operators chapter 7.14 for information on conversions. The L value operand of prefix is decremented analogously to the prefix plus plus operator. When postfix plus plus is applied to an L value, the result is... What's wrong with you? Here is an L value, one value, L value, 1, L. I don't know. 1, L. When postfix, oh, I got it. This is not L. This is 1. Oh God. What is the fundamental difference between letter L and the number 1? I'm so confused. So confused. Okay, when postfix plus plus is applied to an 1 value, the result is the value of the object referred to by the 1 value. After the result is noted, the object is incremented in the same manner as for the prefix plus plus operator. The type of the result is the same as the type of the 1 value expression. When postfix minus minus is applied to an 1 value, the result is the value of the object referred to by the 1 value. After the result is noted, the object is decremented in the manner as for the prefix minus minus operator. The type of the result is the same as the type of the 1 value expression. An expression preceded by the parenthesized name of a data type causes conversion of the value of the expression to the named type. This construction is called a cast. Type names are described in chapter 8.7. The size of operator is the size in bytes of its operand. A byte is undefined by the language except in terms of the value of size of. However, in all existing implementations, a byte is the space required to hold a char. When applied to an array, the result is the total number of bytes in the array. The size is determined from the declarations of the objects in the expression. This expression is semantically an integer constant and may be used anywhere a constant is required. Its major use is in communication with routines like storage allocator and x-natural systems. The size of operator may also be applied to a parenthesized type name. In that case, it yields the size in bytes of an object of the indicated type. The construction size of is taken to be a unit, so the expression size of -2 is the same as size of. So complicated. 7.3 Multiplicative operators. the multiplicative operators asterisk, divide, and percent group left to right. The usual arithmetic conversions are performed. The binary asterisk operator indicates multiplication. The asterisk operator is associative. The asterisk operator is associative, and expressions with several multiplications at the same level may be rearranged by the compiler. The binary divide or division operator indicates division. When positive integers are divided, truncation is toward 0, but the form of truncation is machine dependent if either operand is negative. On all machines covered by this manual, the remainder has the same sign as the dividend. It is always true that this is equal to A if B is not 0. The binary percent operator yields the remainder from the division of the first expression by the second. The usual arithmetic conversions are performed. The operands must not be float. Seven point four. Additive operators. Additive. 7.4. Addition. Additive. 7.4. Additive operators. The additive operators plus and minus group left to right. The usual arithmetic conversions are performed. There are some additional type possibilities from each operator. The result of the plus operator is the sum of the operands. Pointer to an object in an array and a value of any integer type may be added. The latter is in all cases converted to an address offset by multiplying it by the length of the object to which the pointer points. The result is a pointer of the same type as the original pointer and which points to another object in the same array, appropriately offset from the original object. Thus, if P is a pointer to an object in an array, the expression P plus 1 is a pointer to the next object in the array. No further type combinations are followed by No further type combinations are allowed for pointers. The plus operator is associative, and expressions with several additions at the same level may be rearranged by the compiler. The result of the minus operator is the difference of the operands. The usual arithmetic conversions are performed. Additionally, a value of any integer type may be subtracted from a pointer, and then the same conversions are for addition applied. Two pointers to objects of the same type are subtracted. The result is converted by division by the length of the object to an end representing the number of objects separating the pointed to objects. This conversion will in general give unexpected results unless the pointers point to objects in the same array, since pointers even to objects of the same type do not necessarily differ by a multiple of the object length. 7.5 Shift operators. The shift operators, left shift and right shift, group left to right, both perform the usual arithmetic conversions on their operands, each of which must be integer. Then the right operand is converted to int. The type of the result is that of the left operand. The result is undefined if the right operand is negative or greater than or equal to the length of the object in bits. Value of uppercase E1, left shift uppercase E2 is E1, interpreted as a bit pattern. Left shifted uppercase E2 bits, vacated bits are zero filled. The value of uppercase E1, right shift uppercase E2 is E1, right shifted uppercase E2 bit positions. The right shift is guaranteed to be logical, zero field if uppercase E1 is unsigned, as well as it may be and is on the PDP 11 arithmetic filled by a copy of the signed bit. 7.6 Relational Operators. The relational operators group left to right, but this fact is not very useful. A less than B less than C does not mean what it seems to. The operators less than, greater than, less than or equal to, and greater than or equal to all yield 0 if the specified relation is false, and 1 if it is true. The type of the result is int. The usual arithmetic conversions are performed. Two pointers may be compared. The result depends on the relative locations in the address space of the pointed to objects. Pointer comparison is possible only when the pointers point to objects in the same array. 7.7 Equality operators. The equal to and the exclusive not equal to operators are exactly analogous to the relational operators except for their lower precedence. Thus, A less than B equal C less than D is 1 whenever A less than B and C less than D have the same truth value. A pointer may be compared to an integer, but the result is machine dependent unless the integer is a constant 0. A pointer to which 0 has been assigned is guaranteed not to point to any object and will appear to be equal to 0. In conversational usage, such a pointer is considered to be null. 7.8 Bitwise and operator. The ampersand operator is the ampersand operator is associative, and expressions involving ampersand may be rearranged. The usual arithmetic conversions are performed. The result is the bitwise and function of the operands. The operator applies only to integer operands. 7.9 Bitwise exclusive OR operator. The yield operator is associative, and expressions involving yield may be rearranged. The usual arithmetic conversions are performed. The result is a bitwise exclusive OR function of the operands. The operator applies only to integer operands. 7.10 Bitwise inclusive OR operator. The bar operator is associative and expressions involving bar may be rearranged. The usual arithmetic conversions are performed. The result is a bitwise inclusive OR function of its operands. The operator applies only to integer operands. 7.11 Logical AND operator. The Ampersand operator groups left to right. It returns 1 if both its operands are non-zero. 0 otherwise, unlike Ampersand guarantees left to right evaluation. Moreover, the second operand is not evaluated if the first operand is 0. The operands need not have the same type, but each must have one of the fundamental types or be a pointer. The result is always int. 7.12 Logical OR operator. The bar operator groups left to right. It returns 1 if either of its operands is non-zero and 0 otherwise, unlike bar guarantees left to right evaluation. Moreover, the second operand is not evaluated if the value of the first operand is non-zero. The operands need not have the same type, but each must have one of the fundamental types or be a pointer. The result is always int. 7.13 Conditional operator. Conditional expressions group right to left. The first expression is evaluated, and if it is non-zero, the result is the value of the second expression, otherwise that of third expression if possible. The usual arithmetic conversions are performed to bring the second and third expressions to a common type. Otherwise, if both are pointers of the same type, the result has a common type. Otherwise, one must be a pointer and the other the constant 0, and the result has the type of the pointer. Only one of the second and third expressions is evaluated. 7.14 Assignment operators. There are a number of assignment operators, all of which group right to left. All require one value as their left operand. And the type of an assignment expression is that of its left operand. The value is the value stored in the left operand after the assignment has taken place. The two parts of a compound assignment operator are separated tokens. The two parts of a compound assignment operator are separate tokens. What is this? No. L values. The article before is N, so it's L value. L. L value. It is so complicated. In the simple assignment with equal, the value of the expression replaces that of the object referred to by the L value. If both operands have arithmetic type, the right operand is converted to the type of the left preparatory to the assignment. The behavior of an expression of the form uppercase E1 OP equal uppercase E2 may be inferred by taking it as equivalent to like this. However, E1 is evaluated only once. In plus 2 equal to or minus equal to, the left operand may be a pointer, in which case the integer right operand is converted as explained in chapter 7.4. All right operands and all long pointer left operands must have arithmetic type. The compilers currently allow a pointer to be assigned to an integer to a pointer, and a pointer to a pointer of another type. The assignment is a pure copy operation with no conversion. This usage is non-portable and may produce pointers which cause addressing exceptions when used. However, it is guaranteed that assignment of the constant 0 to a pointer will produce a new pointer distinguishable from a pointer to any object. 7.15 Comma operator. A pair of expressions separated by comma is evaluated left to right, and the value of the left expression is discarded. The type and value of the result are the type and value of the right operand. This operator groups left to right in contexts where comma is given a special meaning. For example, in a list of actual arguments to functions, chapter 7.1, and a list of initializers, chapter 8.6. The comma operator as described in this section can only appear in parentheses. For example, has 3 arguments, the second of which has a value 5. Declarations. Declarations are used to specify the interpretation which C gives to each identifier. They do not necessarily reserve storage associated with the identifier. Declarations have the form. The declarators in the declarator list contain the identifiers being declared. These specifiers consist of a sequence of type and storage class specifiers. The list must be self-consistent in a way described below. 8.1 Storage class specifiers. The SC specifiers are like this. The type-diff specifier does not reserve storage and is called a storage class specifier only for syntactic convenience. It is discussed in chapter 8.8. The meanings of the various storage classes were discussed in chapter 4. The auto-static and register declarations also serve as definitions in that they cause an appropriate amount of storage to be reserved. What's wrong with me? There is some problem with my stomach. I'm sorry, guys. In the external case, there must be an external definition. Chapter 10. For the given identifiers somewhere outside the function in which they are declared, a register declaration is best thought of as an auto declaration, together with a hint to the compiler that the variables declared will be heavily used. Only the first few such declarations are effective. Moreover, only variables of certain types will be stored in registers. On the PDP 11, there are int, char, or pointer. One other restriction applies to register variables. The address of operator Ampersand cannot be applied to them. Smaller, faster programs can be expected if register declarations are used appropriately, but future improvements in code generation may render them unnecessary. Hang on. At most, one SC specifier may be given in a declaration. If the SC specifier is missing from a declaration, it is taken to be auto inside a function. External, outside, exception functions are never automatic. 8.2 Type specifiers. The type specifiers are like this. The words long, short, and assigned may be thought of as adjectives. The following combinations are acceptable. The meaning of the last is the same as double. Otherwise, at most one type specifier may be given in a declaration. If the type specifier is missing from a declaration, it is taken to be int. Specifiers for structures and unions are discussed in Chapter 8.5. Declarations with type diff names are discussed in Chapter 8.8. 8.3 Declarators. The declarator list appearing in a declaration is a comma-separated sequence of declarators, each of which may have an initializer. Initializers are discussed in Chapter 8.6. The specifiers in the declaration indicate the type and storage class of the objects to which the declarators refer. Declarators have the syntax. The grouping is the same as in expressions. 8.4 Meaning of declarators. Each declarator is taken to be an assertion that when a construction of the same form as the declarator appears in an expression. It is an object of the indicated type and storage class. Each declarator contains exactly one identifier. It is this identifier that is declared. If an unadorned identifier appears as a declarator, then it has the type indicated by the specifier heading the declaration. A declarator in parentheses is identical to the unadorned declarator. but the binding of complex declarators may be altered by parentheses. See the examples below. Now imagine a declaration where uppercase T is a type specifier like int, etc., and uppercase D1 is a declarator. Suppose this declaration makes the identifier have type where type ... t, where the ... is empty if D uppercase D1 is just a plain identifier. So that the type of lowercase x in int lowercase x is just int. Then if uppercase D1 has a form like this, the type of the contained identifier is ... pointer to D. If uppercase D1 has the form like this, then the contained identifier has the type ... function returning uppercase T. If uppercase D1 has the form like this or like this, then the contained identifier has type ... array of uppercase T. In the first case, the constant expression is an expression whose value is determinable at compile time, and whose type is int. Constant expressions are defined precisely in chapter 15. When several array of specifications are adjacent, a multidimensional array is created. The constant expressions which specify the bounds of the arrays may be missing only for the first member of the sequence. This addition is useful when the array is external and the actual definition, which allocated storage, is given elsewhere. The first constant expression may also be emptied when the declarator is followed by initialization. In this case, the size is calculated from the number of initial elements supplied. An array may be constructed from one of the basic types, from a pointer, from a structure or union, or from another array to generate a multi-dimensional array. Not all the possibilities allowed by the syntax above are actually permitted. The restrictions are as follows. Functions may not return arrays, structures, unions, or functions, although they may return pointers to such things. There are no arrays of functions, although there may be arrays of pointers to functions. Likewise, a structure or union may not contain a function, but it may contain a pointer to function. As an example, the declaration like this declares an integer I, a pointer IP to an integer, a function f returning an integer, a function FIP returning a pointer to an integer, and a pointer PAFI to a function which returns an integer. It is especially useful to compare the last two, the binding of like this, so that the declaration suggests and the same construction in an expression requires the calling of a function FIP and then using indirection, though the pointer result to yield an integer. In the declarator like this, the extra parentheses are necessary, as they are also in an expression to indicate that indirection, though through a pointer to a function, yields a function, which is then called. It returns an integer. Is another example like this. Okay, hang on. Here is the time for me to take a break. Goodbye, everyone.